All right, today we're going to be talking about volumes of solids and of revolution by disks or washers. We'll talk about what the disk or washer means, but basically what we're doing is we're going to look at taking a function and rotating it either around the x-axis or possibly the y-axis or maybe even another function somewhere. Okay, so maybe a vertical line or a horizontal line. So when we look at this function here, this is the function y equals 3x. And if we were to graph that and shade it in, we could find the area under this very easily. But now what we want to do is we want to take this line and we want to rotate it around the x-axis. And so if you do that, if you look down here on the bottom, you've got this function that's coming out from 0 to 1. And then you're going to rotate it around the x-axis this way. All right. And when you do that, you create this triangular prism here. And if you were to slice that, you see the yellow part here in the slice, if you were to slice that, you would end up with a solid disk. Okay, and so those disks that we would slice through are perpendicular to the x-axis. Okay, so what we're going to want to look for is what's the volume of that cone that's generated there. Likewise, on the right side, it doesn't have to go all the way back to the x-axis, so we could have an area that's bounded by this graph of y equals x cubed and the y-axis right here, and you can see the arrow here. We're going to take this and we're going to spin it around the y-axis, okay, and it's going to generate the solid that you see below. And again, if we were to take and slice this solid straight across perpendicular to the y-axis, we would end up with this little disk in here. Okay, you would end up with a solid disk in there. Okay, I think the next page kind of says the same thing. It talks about the cone again and y equals x, so very similar one to that, but it actually gets into more depth on how do we actually find the volume then. So when we rotate around the x or the y-axis, we're going to create some sort of a solid. Okay, sometimes these solids have, when we slice them, you get what's called a disk, which is a solid circle. Okay, and that solid circle, the disk, is just a circle. So again, if we were to slice this thing right through here, or even if you look down here, you can see the slice and the circle that's around there. Well, the area of that circle is just pi r squared. Okay, and then imagine an infinite number of those circles, you know, all stacked up on each other. Obviously I can't draw them stacked up on each other, but imagine an infinite number of those just all stacked together now. Okay, as you do that, as you stack an infinite number of those together, you're taking the integral of the area function. Okay, so the integral of the area of that disk from a to b, which in this case our b is right outside here, and you can see that in the last example it was 0 to 1. Okay, so we can integrate that, and in doing that we can always pull the pi outside the integral here, and then it's just a matter of integrating from 0 to b of x squared dx, and we all know how that's done by doing an antiderivative and then plugging in the upper and the lower limit here. Okay, so sometimes when you spin a function around the x or the y-axis, you get a solid disk. Other times when you spin, you might get what's called a washer. Okay, so this one is the washer method. So we're talking about what if we want the volume between two functions. Okay, so this is if you look at the graphs here, I'm going to shade in, do a little bit of shading and drawing here. So if I were to shade in this region in here, so we talked about how to find the area between these two graphs, the upper minus the lower and that kind of thing. And so now we're going to talk about how to find the volume if we take that and we spin it around the x-axis again. So we want to take this and spin it around the x-axis, and it's going to create this picture that you see down here below. Now what you want to look closely at is when you look at this picture, this curve of y equals x cubed here, it's going to leave a little sort of a divot in that solid, because as you spin it, it's going to have an open part right here at the top, and then it's going to get more solid and filled in as you go down. And what happens when you slice that is you end up with a disc with another hole in it, and we call that a washer. Okay, so if I were to slice this thing perpendicular to the x-axis, straight up and down, I would end up with this washer, and I want to find out how to integrate and find the volume of this new solid. This new solid, again, it's not just a rectangular, or excuse me, a triangular prism with a circular base. It's actually got some space in the middle, more like almost like a cup or something, you know, like a snow cone cup or something like that. Okay, so when we find the area, we need to look at not just, you know, what's the integral from 0 to b. Again, if this was b out here on the x-axis, we need to look at subtracting that inside area of that washer. Okay, so we just want to find the volume of all of this blue shaded area on these washers. And so now we're going to look at it in terms of what's the radius of the larger portion. So that's always from the center to the outside of the function. All right, and then we're going to subtract. So this is r squared right here. So the area of that large portion, that largest circle there, would be pi capital R squared. And then we need to subtract out whatever is in this non-shaded area in the center of that washer, and so we call that little r squared. And the area inside there is just pi times little r squared. The area of the washer, of the big disk itself, is pi times capital R squared. So that's what we're going to look at today as we play around with some of these guys. And let's take a look at this first one. Now, again, what you have to picture here is that all we're doing is just taking some sort of a function and rotating it around the x-axis. And so, again, if you visualize a large disk being cut out of this, okay, that's what the picture on the right shows over here, is this orange disk that's been cut out. Now, this disk is rather thick, so if you were to stack them up, you would get this picture on the right side of multiple disks. So you can see that if I went to the next disk, it would be a little bit taller out here maybe. Okay, and then I would fill that in, so that might be, you know, this disk on the right side over here, that might be that disk right there, and so on and so forth. So as those disks get thinner and thinner and thinner, that's what the integral does for us, is it finds the volume as you have an infinite number of thin disks. Okay, so if we're going to rotate something around the x or the y-axis, and the resulting, so we'll say the axis of revolution is the x-axis here, okay, x-axis, and so if the resulting cross-section, okay, so again, when we talk about cross-sections, that's like looking at this one disk right in the middle here. If that resulting cross-section is a solid disk, then we're going to look at it in terms of the integral from a to b of pi r squared, where r is the radius of that disk. Likewise, we can rotate it around the y-axis, and so we would have the axis of revolution being the y-axis. And so if we were to rotate around the y-axis, we would integrate with respect to y. But now, as we look at the radius of this disk being spun, if we look at the top portion here, this is going to be upper minus lower to find that radius. On the lower picture, it's going to be right minus left to find the radius of that disk. Okay? So that's where we're headed today. And when we get to the washers, we'll talk a little bit more about the washers. So we're going to start off with some disks here. All right? So this one says, find the volume of the solid formed by revolving the region bounded by y equals negative x squared plus x and y equals 0 about the x-axis. So the first thing we have to do here is we have to realize that our cross sections are perpendicular to the x-axis. This is important to understand this. Okay, so what they're telling me is that my integral is going to be with respect to x. All right, and so all of my equations need to be in y equals. And in order for me to find that region, the first thing I want to do before I even think about spinning is I got to know what this region looks like. So I'm going to take my my function y equals x squared negative x squared plus x, and I need to graph that. So I'm going to find some x-intercepts here. So we're going to do negative x squared plus x, and if we factor this, we're going to get, I'm actually going to factor out a negative x, so that leaves me x minus 1. So we have x equals 0 and x equals positive 1. Alright, so I have an intercept here, I have an intercept here. This is just an upside down parabola, so it's going to do something along these lines right here. And my goal is to spin this or revolve this around the x-axis. So it's going to revolve like that. And the area that I'm looking to find, or the volume I should say, ultimately, is in there. So you can see the picture off to the right side in red when we spin that thing around. That's what it's going to be. Okay? It's going to create this form right here on the right side. So how do we do this? Number one, we need to find the radius. Well, to find the radius here, we're going to do some upper minus lower. Just like we've been doing. Upper minus lower. Now, the nice thing about this one is the radius is simply, since the lower is 0, then the upper is just the function itself. So my radius, r, is equal to negative x squared plus x. Okay? So when I spin it, the other part will spin down here underneath, and that's why I can do upper minus lower for radius. My limits of integration are going to be from 0 to 1. Okay? X equals 0 to x equals 1. And then we're going to set up the integral by finding the integral, and I'm going to write out the formula again here, of a to b of pi times the radius squared dx. Alright, so let's see. So our limits here, we said were 0 and 1. We have pi times the radius. We said our radius was negative x squared plus x dx. Alright, and we're going to use some calculator here. So if you can put the pi inside the integral, or you can leave it outside. A lot of times you'll see situations like this where they pull the pi outside and they leave the negative x squared plus x inside. And you should be able to integrate this by hand as well. Just no decimal values here. And so if you were to plug this in, and I'm gonna do this first one with you, and then we're gonna I'll leave the rest of them up to you guys to do. So the one thing that I tend to forget in here is I tend to forget the pi on the outside. Okay, so I have a bad habit of doing that. So the first thing I'm going to do is I'm going to punch right away. I'm going to punch in pi and then my math 9. I always want to look, is there something on the outside of that integral that should be in there? So 0 to 1. And we'll plug in our function here, negative x squared plus x. Negative x squared plus x dx. And we'll hit enter. And oh, you know what I didn't do? I just realized I put in my function. What did I forget right here? I forgot to square this. Alright, I knew someone right there. You got to square it. It's times the radius squared. So I'm just going to do this. I'm going to cheat a little bit here. I'm going to hit second in entry. I'm going to bring up my integral again. Now this time I'm going to have to go back and put in some parentheses here. So we're going to have to insert some parentheses here. Right there. And right there. And then a squared. There we go. This should do it. There we go. 0.105. See, that was easy, wasn't it? You just got to get it in there correctly. Oops, wrong button there. Okay. All right. So this equals 0.105. Okay. So the only difference really between what we're doing here and what we were doing earlier in the unit was, now we're not just finding upper minus lower, that we're taking and spinning that around the x-axis, and so we're creating these little circles, and that's why we're using the formula pi r squared here. All right. Okay. So this time we want to find the volume of the solid by revolving the region around y equals sine x and y equals 0 about the x-axis, x from 0 to pi. All right, so sine x, if you remember, it has zeros at 0, it has a 0 at pi, so that's 3.14, which is, right about here. Let's see, halfway through, which is a little over 1.5, we're going to be at 1. And a sine curve does something along these lines here. So it kind of has that same shape as as kind of like a parabola, and then obviously if it came down this way, it would, do something like that. Okay, but we just want to, it says bound by y equals 0, so that's the x-axis. And we're rotating it about the x-axis. So our axis of rotation, our cross sections are perpendicular to the x-axis. That makes a difference when we look at this. As you'll see later, if we were to rotate this about the y-axis, we would end up with not a solid disc, but we would end up with a washer in this case. And we'll see some of those in just a little bit here. The radius, again, is the upper minus the lower. Okay, so upper and lower. Since my lower is 0, the radius is simply the upper function. So my radius is sine x. Our limits of integration are 0 to pi. So we're going to take the integral from 0 to pi of pi times sine of x squared dx. Remember, I forgot the squared on the first one. All right, and let's see here. We're going to pop this one in the calculator, I think, too. So if you go back and do that, again, I would just get in the habit of typing in the pi first, 0 to pi of sine of x squared dx. And if you do that, you will end up with 4.935. Okay? So you should definitely practice those with your calculator and see how those turn out. All right? Number 3, find the volume of the solid formed by revolving the region y equals the square root of x, y equals 1, and x equals 0 about the x-axis. Now you'll notice this little part in parentheses here. It says we have a hole here, so this is a washer problem. So let's graph it and see what we're looking at here. So I'm going to start with y equals the square root of x. So I know that would be here. And since we're going, well, I'm not sure where we're going, so we'll graph through there. Square root function comes up like this. The graph of y equals 1 is this function right here. Y equals 1. And so we have y equals the square root of x. And so this time, again, we're going to revolve around the x-axis, so we're going this way. Now imagine, we take this shaded region right up here, okay, and we spin that around the x-axis. What's going to happen is all of this stuff in this area right here, this purple area that I'm shading, this is going to create a hole as we spin it. And you can see the picture off to the side here. If you look at this spinning around on a blown up picture, again, it's sort of like a cup as it goes to the inside of the spin right here. It sort of creates this cup, and if you cross section that, you get what we call a washer. Okay? Now, how do I know that I'm going to get a washer? Just by looking at the picture of the graph, because whatever axis I'm spinning to, so if I'm going to spin around the x-axis, if I go perpendicular to the x-axis from the top, and I can do perpendicular to the x-axis from the other equation as well. If those two are different radii, then what we have here is we have a big R and a little r, And the little r, when you go to spin this, that was that picture we saw a little bit ago where we had that washer. Okay, love my picture there. So capital R is the distance from the center, in this case the center being our x-axis, and the outside of the function, that's y equals 1, whereas little r is the distance from the center being our x-axis out to the closer function, you could call it in this case, the closer function, which is y equals the square root of x. Okay, so our cross sections are perpendicular to the x-axis, so we're going to want to make sure we're setting this up with respect to x. If I can draw this here, x-axis. We want to find both radii, so capital R here, our big R, is going to equal 1 take away 0. So again, hopefully you can see that very easily there. Our capital R is 1. And then our lowercase r is the distance from basically the function that's closer to the y-axis. So our little r is the square root of x minus 0. Okay? Our limits of integration are 0 to 1 because they told us that we're going between this curve and these two curves intersect at 1. So we're going from 0 to 1, and then we'll set up our integral. So we have 0 to 1. I'm just going to put the pi on the outside right away. And this time we're doing r squared, capital R squared, minus lowercase r squared. Well, capital R squared is just 1 squared, minus lowercase r, which is the square root of x squared, dx. And we'll do pi from 0 to 1. This is 1 minus x dx. And since this is pretty easy, we'll just go ahead and finish this one. Oops, we don't want that. We want an antiderivative. So we have pi times x minus x squared over 2. And we're going from 0 to 1. So this is going to equal, and I'm going to leave pi on the outside, pi times 1 minus 1 squared over 2 minus pi again times 0 minus 0 squared over 2. All right, now this one's pretty easy to simplify. The whole right side is 0, and inside the parentheses here we have 1 take away a half, which is a half, so we end up with pi halves here. Okay, so the area under that curve is just pi halves, no big deal, right? All right, let's take a look at some other ones here. What else we got? Okay, so find the volume of the solid formed by revolving the region bounded by y equals x squared plus 1, y equals 0, x equals 0, and x equals 1 about the y-axis. Okay, so as soon as it says about the y-axis, I know that my cross sections are perpendicular to the y-axis, which means my limits of integration have to go with y values now, not x values. So let's graph both of these, all of these, I guess. So y equals x squared plus 1 would look like this. Okay, and I know that because of the way parabolas graph that it's going to hit negative 2, 1, or excuse me, negative 2, 2, and positive 1, 2, negative 1, 2, and positive 1, 2. Our next function is y equals 0, so that's the x-axis. X equals 0, which is my y-axis, and x equals 1. So we're going to take this function right here, and again, this is my bound between these two guys here, and y equals 0 and x equals 0. So this is the area that I want to rotate here. So in this case here, I'm going to draw a third piece in here, and I'm just going to draw a dashed line right across here. And the reason I'm doing that is because if I revolve that bottom part around the y-axis, so remember we're going around the y-axis, if I revolve that bottom part, that's a solid, and its cross sections would also be solid. So if I were to cut through here, it would be a solid disc as we rotate it around. But on the upper part here from 1 to 2, we've actually got a washer situation again. So because we can see a big R here and a little r here, that means that we have a washer there. Whereas on the bottom part, all we see is R. Okay, so we're actually going to have what we typically call a lowercase r for the bottom part, and then we have uppercase R and lowercase r for the top portion. All right, so our first integral is just going to go from 0 to 1. Okay, so we're going on the y-axis 0 to 1. We got our pi outside here, and this is going to be the function. This is x equals 1, so this is 1 dy. That one's going to be tough, huh? Plus pi again times the integral from 1 to 2, and this time we have to be a little bit more careful here because our first function, the radius, the capital R, again is going to be 1 take away 0, which is 1 squared, minus little r squared, and little r squared is x squared plus 1 dy. Okay, oh, you know what? It's not x squared plus 1, because I just noticed that I had x squared and dy. We can't do that, can we? All right, so because we're going around the y-axis, we're perpendicular to the y-axis, I need to solve this equation, y equals x squared plus 1. Need to solve this for x. So we're going to subtract 1, that's going to be y minus 1, equals x squared. If we square root both sides, that's the square root of y minus 1, both positive and negative, equal to x. And since we're looking at the right side of the parabola here, that's the positive root. So this is actually going to be the positive root is, so capital R doesn't change, but little r is actually the positive root of y minus 1. Okay, so I knew something was wrong there when I had x's and y's in there. So I forgot I was going perpendicular to the y-axis. All right, and so this one's one of those that you can do by hand again. I would definitely encourage you to do this by hand. Oh, it looks like we got enough room, so we'll go ahead and do this. So I'm going to take the antiderivative of 1, which is just going to be y. So this is pi times y from 0 to 1. That should be pretty easy. Plus, and what did I forget over here? I forgot to square this dude, didn't I? Yep. So again, I just need to slow down a little bit here. This is capital R squared minus little r squared. All right. Just like the one on the right side here, this is still r squared. Okay, so if it helps, I should put that in there for now, I guess, too, even though 1 squared is the same. All right, so I'm going to simplify this integral a little bit here before we go on anymore. This is going to be 1, what do we got here, minus, if you square this, we're going to get y minus 1. So this actually turns out to be 1 plus 1, which is 2 minus y. So this is the integral of 2 minus y. That's what I need the antiderivative for. So we've still got our pi out here. And the antiderivative is going to be 2y minus y squared over 2. This one's going from 1 to 2. And let's go, here we go. On the left side, pi times y, we plug in 1, we get pi times 1 minus pi times 0. Obviously that part's going to be 0 plus pi times 2 times 2 minus y squared, oops, excuse me, 2 squared over 2. And we're going to have to subtract, which means I'm going to need another set of parentheses here, subtract, plugging in for 1, 2 times 1 minus 1 squared over 2. Okay, now this one actually simplifies pretty easily too, because we got pi here plus pi times, inside here we're going to get 4 minus 2, which is going to be 2, minus, and this is 2 take away a half, which is 1 1/2 or 3/2. So 2 minus 3/2 is a half, so this is pi plus pi over 2. All right, and actually we can add those together. That would be 2 pi over 2. So this would end up being 3 pi over 2. All right, I think that's pretty straightforward. Hey, is that it? Are we done? Oh, look at that. We are done. There you go. Have fun.